This video explores electronic coupling in quantum mechanics. It is the fundamental engine of electron transfer theory, bridging abstract quantum states and rational molecular design. Key to this is the coupling matrix element, H12 or HAB. Coupling is the mathematical driver of charge mixing. The core definition is that electronic coupling is the off-diagonal matrix element of the electronic Hamiltonian between two diabatic charge localized states. The key insight is that coupling causes the mixing, driving intervalence charge transfer, and avoided crossings. The two-state Hamiltonian isolates coupling as the off-diagonal element, HDA. Charge delocalization is not set by coupling alone, but is determined by the ratio of coupling to detuning. Strong hybridization requires large coupling and a small energy mismatch. Diabatic states provide chemical transparency for electron transfer, maintaining a stable chemical identity. Adiabatic states are eigenstates of the electronic Hamiltonian, excellent for spectroscopy, but their character changes rapidly near avoided crossings. In electron transfer, we typically care about how a localized charge moves. Coupling dictates the size of the avoided crossing gap, which is proportional to twice the magnitude of HDA. This leads to two regimes of transfer: non-adiabatic or weak coupling, where the system stays on the original diabatic state, and adiabatic or strong coupling, where the system follows an adiabatic surface, smoothly redistributing charge. The electron transfer rate, K sub ET, scales with the square of the coupling, represented by the magnitude of HDA squared. In the non-adiabatic regime, doubling the coupling increases the transfer rate roughly fourfold. The classical Marcus limit is controlled by three master knobs: electronic coupling, H sub dA, total reorganization energy lambda, and the driving force delta G. Coupling is essential, but it is only one of these three factors controlling the reaction landscape. The primary design lesson is not to optimize coupling in isolation. Success requires a favorable combination of sufficiently large coupling, appropriately small reorganization energy, and favorable energetics. Focusing solely on coupling risks building a system where forward transfer and backward recombination are equally fast. Microscopic determinants of coupling include orbital overlap and distance. Coupling relies heavily on overlap and phase symmetry. Misaligned or out-of-phase orbitals can cause coupling to shrink or cancel. Coupling decays approximately exponentially with distance in the tunneling or superexchange regime. When donor and acceptor are not directly adjacent, coupling arises virtually through bridge states, called bridge-mediated superexchange. Key variables include the energy gap, lower-lying virtual bridge states, and smaller donor bridge energy gaps, which dramatically enhance communication. Other microscopic determinants are dynamic disorder and spin. Coupling is not a static constant. It fluctuates due to thermal motion and torsional fluctuations. In open-shell systems, the spin state fundamentally changes the spatial extent of the density, altering overlap and coupling independently of distance. Coupling is rarely measured directly. It is inferred from spectroscopic and kinetic data, such as intervalence charge transfer spectra. The Robin-Day classification system categorizes systems from Class 1, weakly coupled, localized charge, to Class 3, strongly coupled, fully delocalized charge. Calculating coupling requires carefully built diabatic states. The generalized Mulliken-Hush approach transforms adiabatic states into charge-localized diabatic states. The absolute value of coupling depends heavily on exactly how the diabatic states are built, making the theory technically demanding. The ultimate goal is rational molecular scale design. A deep understanding of coupling enables an engineering approach to molecular electronics and photochemistry. Researchers can use computational methods to screen molecular pairs, crystal packings, and donor-acceptor frameworks before stepping into the lab.